Here again, we see our skateboard flow: assembly, sand, and paint. We have the raw materials, the inputs to the system, the deck, the board, and the trucks. And this is called the bill of materials, or BOM. We need to meet our customer demand. So what decisions and information do we need to make this happen? Normally, demand is given as a forecast from the customer. And here we see the demand forecast from sports retailers for 3 different models of skateboard. At the beginning of the year, there's no real demand for skateboards. But as we move into the springtime, the demand increases from about 65 here in March to 100 in April, over 200 in May, over 300 in June, and then dropping off in July and August. Customer forecast generally will cover a period of time. Here we see for the entire season. And we need to order our bill of materials in time to produce a skateboard so that they're ready to be shipped according to the forecast. At least the forecast is the best information we have at the current time. So the flow is that the retailer forecast will arrive for the skateboards for all the different models. Then this has to go into the systems, to the planning system, so that the components can be ordered. These will be ordered then according to the lead times that they require, and they will then be ready for production of the skateboards, and then those can be shipped to the retailers according to their forecast. Now, how do we manage this? How do we do this production planning? Let's go through the classical production planning flow in a company. Based on the forecast, the first step is that an aggregate production plan is developed. This aggregate plan specifies monthly outputs in aggregate quantities rather than specific product types. This aggregate plan is a midterm plan, typically up to 18 months, maybe 2 years, and it considers things like pooled capacities and works in time buckets, which are generally monthly. Like, for example, here's our skateboards. Instead of seeing the 3 different models, we have them aggregated, all models, into demand by month. And again, sometimes some smoothing of the demand. You see roughly the same type of demand figures going up to a peak in June and then down again in July and August. Now, the aggregate plan is considering things such as strategic plans from the business unit. It's looking at the overall capacity plans, the supply sources that are available, and it's looking at costs. So in other words, the capacity and the production can be secured to meet the forecasted demand, but planned efficiently. So aggregate plans, for example, they plan production levels, inventories, they look at the workforce size, they decide if they're going to do outsourcing, they decide if they're going to have to hire or fire anybody, overtime, undertime, and so forth. From the aggregate plan, then, the master production schedule, or MPS, is designed. The MPS disaggregates the aggregate plan, giving the quantity and timing of specific end items for a scheduled planning horizon. And this is generally shorter than the aggregate plan's horizon. And it accounts for actual customer orders, updated forecasts, known capacity constraints, etc., etc. And assuming these are small, then the material master production schedule will then equal the aggregate plan. And so for our skateboards, what we see here for the MPS is we've disaggregated the demand into our 3 different models again. And here we're looking at a shorter time period. We're looking in weekly buckets. And you may also notice in this example, we're talking about fiscal calendars. We're actually talking about the financial week planning, which is done in the production. And so here we can see then that the total quantities roughly are matching our master production schedule. From the master production schedule, we can finally decide what materials need to be ordered and when, and this is the role of material resource planning, or MRP. Material resource planning takes the master schedule and develops a detailed timetable for ordering the bill of materials, or the BOM, the items that go into making the product as we showed. The MRP also looks at the inventory record file. It needs to know what the BOM is. It looks at the inventory record file to see how much inventory, these raw materials, for example, we have on hand, how much to order, lead times, lot sizes for ordering, etc. And the MRP will then generate order schedules for the materials, inventory levels and production control information, and of course purchase orders to suppliers for actually ordering the raw material. It also creates additional reports which are then used for planning and controlling. And now what's important here is that the MRP is an essential tool for production. It keeps track of inventory in a complex system. It triggers orders for raw materials to meet the end forecasted demand. Now there's some pitfalls to the MRP which you would study in a course about this. It doesn't take into account, for example, variability. It assumes the lead times are fixed, it assumes the process times are fixed, and also fixed lead times for the raw material deliveries. It also assumes an unlimited capacity and is limited in the way it treats rework, for example. But what's important to realize that the MRP has played and still plays a very established role in production today. But let's look at this in terms of our push-pull concept. So we go back to our definition. A pull system establishes an a priori limit on the work in progress, while a push system does not. Now we can now see that an MRP, which is based on forecast, is a push system. And if we continue to quote from factory physics, the MRP is scheduling the release of work based on, can be the actual demand, but the forecasted demand, the actual and forecasted demand for a period of time. Whereas a pull system authorizes production based on the status of work in progress throughout the plant, and thus controls the work in progress and the inventory in the production. This limitation on the amount of WIP that can accumulate in a production system is the key distinction between the push and pull, and is necessary for enabling JIT production. So if we look at this in terms of significance for lean production, we've already said that just-in-time production is one of the key elements of quality control in lean production, producing only what is needed, when is needed, and the quantity needed. However, as the 3 M's emphasize, JIT is not easy in a complex system, and a stable pull system is required to target JIT. JIT will seek to reduce any additional inventory in the system, not only from the end products, but also upstream in the process, including work in progress and buffer stocks. This results in a reduced flow time and faster than identification of process problems, which leads to improved processes and less variability, which reduces our waiting times, which improves our continuous flow. And we go back to step 2, where we have a stable pull system. We can continue this type of cycle. So in the next lecture, what we're going to look at is how to realize a pull system in order to support lean production.